I want to talk about curve sketching of a different type of functions. Last time, basically, the method we talked about last time will basically work for any polynomial. Let's talk about curve sketching with asymptotes. This method will work for anything which looks like a fraction of a polynomial divided by a polynomial. The only extra business is, I gave you some steps last time. The steps were find the critical numbers, do the increasing, decreasing intervals, and then plot the critical numbers with their y values, and then connect the dots. Curve sketching with asymptotes is the same, only you can do this before you do anything else. I'll just say first, find the asymptotes. And then when you draw the curves at the end, the curves must fit the asymptotes. All right? You'll see what I mean by this at the end. If you have an asymptote, the curve has to approach the asymptote and not cut through it. All right? Let's just try an example. How about f of x equals, I'm going to do 4 minus x divided by x. All right? This is a function which will have asymptotes. How do you find the asymptotes? I just said, first, find the asymptotes. This isn't really something that we've talked about before, but how you find the asymptotes? Vertical asymptote. To find a vertical asymptote, you check when the denominator equals 0. And to find the horizontal asymptote, this would be where does the curve go to when the x increases forever? Does it actually go to a particular value? To find the horizontal asymptote, you do the limit as x goes to infinity of f of x, right? That is, if I consider the values of x to be really big, where does the y value go to? That's what a horizontal asymptote means. Okay? This is something we talked about how to do a very long time ago, but I hope you remember. If you don't remember, it'll only take you a moment to remember because there was a very awesome trick to do that. Let's try and do this for this example here. Four minus x over x. So for a vertical asymptote, the vertical tote, we have to find all values which make the denominator equal to 0. Well, the denominator simply is x. So x equals 0 is the value. So the reason I said that is because this makes the denominator equal 0, right? What about horizontal asymptote? As I said, we must find the limit as x goes to infinity of f of x, which is 4 minus x divided by x. And what is this limit? For this, you got to remember those rules. This was in the second week of class we did this. The rules for the limit as x goes to infinity. You look at the degrees on the top and the bottom. Remember this thing? If the degree on top is bigger, the limit does not exist, which means there is no horizontal asymptote. If the degree on the bottom is bigger, the limit is 0, which means the horizontal asymptote is y equals 0. If the degrees are equal, which they are in this case, the limit is equal to the ratio of the coefficients in front of the highest degree term. So in this case, that ratio would be minus 1 over 1. Minus 1 is the coefficient on x up top. 1 is the coefficient on the bottom. So minus 1 is the answer. So there's a horizontal asymptote at y equal minus 1. You will see this when we eventually draw the graph. All right. Anyway, having done that, we are still going to do all the same other stuff. So I'm going to find the critical numbers, do the chart with the increasing, decreasing, etc. All right, critical numbers, you look at this thing and you need to, first of all, take the derivative. All right. What am I going to do to take the derivative here? I think I better use the quotient rule, right? That being a quotient, you're going to have to do the quotient rule. I hope you remember the quotient rule. It is the bottom, x, times derivative of the top. Derivative of 4 minus x will be minus 1. Minus the top, times derivative of the bottom, which is 1, divided by the bottom squared, x squared. All right, can we simplify? I think so. This is minus x, and then minus, this times 1 doesn't do anything. I distribute the minus. It looks like minus 4 plus x over x squared. Minus x plus x will cancel. This is negative 4 over x squared. All right, that is fairly simple. Maybe I'll put it up here. Excellent. F prime of x is minus 4 over x squared. We got to do the critical numbers now. Set this equal to 0 and also discuss when this does not exist. So f prime equals 0. I go minus 4 over x squared equals 0. Solve for x. I'm going to multiply the denominator across. It'll say minus 4 equals x squared times 0. Actually, that's 0. Minus 4 equals 0. Remember what to do when you see some nonsense like that? Your conclusion here is there is no, obviously this is not possible, which means it is not possible for the first derivative to equal 0. So this f prime equals 0, never. There are no such values that make f prime equal 0. All right, what about f prime dne? There is a value which makes f prime not exist. You got to say, again, where's the denominator equal to 0? In this case, x squared is the denominator equals 0. Take a square root, you get x equals 0. All right, so we have one critical number. It is when x equals 0. Let's make the chart. All right, the first derivative does not exist when x equals 0. Let's plug number bigger, number smaller. So I'm going to do f prime of 1. Using f prime now, negative 4 over 1 squared. This is negative 4, which is negative. And down here, back here, I'll do f prime of minus 1. This is negative 4 over minus 1 squared, which is also minus 4, which is also negative. All right, this is my increasing and decreasing chart. So we have one critical number. The derivative does not exist. Let's plot all the critical numbers. So I'm going to find the y values. X equals 0 has y equals f of 0, which is, I go back to my original formula, f of 0. 4 minus 0 divided by 0, which is 4 divided by 0. What does that mean? This is a DNE, right? So actually, this point, this x value is a critical number, but it doesn't even have a y value at that point. All right. Let's see if we can graph this thing. All right, let's try and graph this. Before I try and plot any points or anything, first I'm going to draw the asymptotes. Remember, we had a vertical asymptote at x equals 0, which would be right along the y-axis. I'm going to put it sort of next to it so you can still see it. All right, a vertical asymptote right there, and horizontal asymptote at y equal minus 1, which is here. All right. Okay, those are the asymptotes. Next, we should plot the critical numbers with their y values, but actually there are none. There's a critical number, x equals 0, but it has no y value. So we, unfortunately, have nothing to plot. The last step was connect the dots, although there aren't even any dots. What are we even going to do here? Well, the asymptotes are your friend in this type of example. Check it out. Let's just, pretend like the asymptote is a critical number, and I'm going to think, how do I draw the graph to the right of the asymptote, and how do I draw the graph to the left of the asymptote? Check it out. To the right of the asymptote, remember, the graph must approach the asymptotes. So when this curve leaves the asymptote, I think there are two options, right? Either it should come down like that. Either, this vertical asymptote means when the curve gets close to it, it either goes like up forever or it goes down forever. So when we leave this asymptote, it either is going to look like that or it's going to look like that, right? Because that's how a vertical asymptote works. Things, when they approach it, either go up forever or they go down forever. And when we go further and further to the right, this graph must approach this line. Now, it might approach from below, so it might come like that, or it might approach from above, like that. So really, we only have two options. Either it comes down sort of up from up above, down from heaven and approaches this line, or it comes like up from hell, like a bat out of hell, and approaches this line. Which is it? Again, we take a look at the chart of the increasing, decreasing. That's why we did this chart, because it will help you answer. Which is it? Is it the one which ascends from below, or is it the one which descends from above? Well, to the right of 0, this function is supposed to be decreasing, and so it must be this one and not this one. So I'm going to erase this one. It is not that one. It is this one here. So the graph does that. All right? The asymptotes help you out, actually. They tell you what the shape needs to be. Oh. You. It looks like that. It comes from above, decreases, and to the asymptote. All right? These asymptotes actually help you out. They help you to decide what the graph has to look like. What about to the left of the asymptote? Again, because of this sort of, crossing asymptotes, there are only two options. It either does this or it does this. And which one is it? Check it out. It says the graph to the left of the asymptote is decreasing. That one is increasing. That one is decreasing. It must be that one and not that one. So I'm going to erase that one. It is that one. And that's it. This is the graph of the function. Let's do one more. F of x equals 3x squared over x squared minus 4. All right. Just like last time, I'm going to begin by finding the asymptotes. So vertical tote. Remember this one, we set the denominator equal to 0 and solve for x. X squared minus 4 equals 0. This you could factor or you could take a square root, right? I'll do it that way. X squared equal 4. Square root on both sides, x equal plus or minus 2. All right. So those are some vertical asymptotes. We have two vertical asymptotes at x equal negative 2 and x equal positive 2. Is that even possible? Two vertical asymptotes? Yes, possible. All right. What about horizontal asymptote? For that, we take the limit as x goes to infinity of this thing. 3x squared over x squared minus 4. Remember your trick. This one, the degrees are equal on top and the bottom, and so the answer is the ratio of the coefficients, which will be, in this case, 3. All right, so when you draw your graph, it's going to have two vertical asymptotes and the one horizontal asymptote. Let's find the critical numbers. We got to take the derivative. Unfortunately, we have to use the quotient rule again. We're going to go bottom, and square minus 4, times derivative of the top, which is 6x, minus the top, 3x squared, times derivative of the bottom, which is 2x. All of this divided by the bottom squared, x squared minus 4 squared. All right, let's simplify as much as we can. Actually, I'm not going to touch the bottom. This is not going to get any simpler on the bottom. You could expand it out, but that doesn't help. On the top, we should distribute that. So it's going to be 6x cubed minus 24x, right? And then minus, multiply these guys, 6x cubed. Isn't that nice? Those 6x cubes are going to disappear. Okay, cancel these guys. And that's as simple as that's going to get. So I'm going to put these over here like I do. All right, let's find the critical numbers. We set the derivative equal to 0. We get minus 24x over x squared minus 4 whole thing squared equals 0. Multiply this denominator over there. It becomes 0 again, so it's just minus 24x equals 0. Divide the 24. X equals 0. Okay, that's one critical number. Let's also plug in, let's also say when the derivative does not exist. This is the other way to find critical numbers. When the derivative does not exist, that would be when the denominator is 0. X squared minus 4 squared equals 0. Square root to get rid of that 4. And actually, this is the same as when we found the vertical asymptote, isn't it? We're going to get x equal plus or minus 2. So this is actually not a coincidence. It's always a fact that when there's a vertical asymptote, the derivative will not exist. If you are checking when the derivative does not exist, if there's a horizontal asymptote, that automatically will be a place where the derivative does not exist. So this is not a surprise that the derivative does not exist right there. All right, we're almost ready to start. Let's do the old increasing, decreasing thing. All right, I had 3 critical numbers, 2 of which were DNEs for the derivative, and 1 was equal to 0. Let's plug in betweens. F prime of minus 3, say. I'm using this formula. Make sure you use the right formula for F prime. Negative 24 times negative 3 divided by something squared. It doesn't matter what's down here. It's being squared, so that's going to be positive on the bottom, and this is going to be positive on the top. So this is positive over positive, which is positive. Positive, okay. What about... how about minus 1 here? I get minus 24 times minus 1 divided by, again, something squared will always be positive. So up top, this is, again, positive over positive. Okay, positive. How about f prime of 1? Minus 24 times 1 divided by something squared. This is negative over positive, so that's going to be negative. And finally, I'll use 3. F prime of 3 minus 24 times 3 over some business squared. That, again, is negative over positive, so it's negative. All right, there's my chart for the first derivative, increasing, decreasing. I think we're almost ready to draw the picture. We just need some y values first. So to find the y values for each critical number, x equals 0 for the y value for that one. I go f of 0. I get, plugging in here, make sure you use the right formula, 3 times 0 squared over 0 squared minus 4. This is 0 over negative 4, which is 0. Okay, so I guess x equals 0, y equals 0 is one of the critical numbers to plot. These other ones, they have y values which don't exist because they are on the vertical asymptotes, right? If you plug these other ones in, x equal minus 2 and x equal plus 2 are vertical asymptotes, so they will have no values to plot. So this is the only value that I'm going to plot. 0, 0. Let's do it. First, we'll draw our asymptotes. They were at plus 2 and plus minus. Plus 2 and minus 2. Those are the vertical asymptotes. Plus 2, minus 2. And then I had a horizontal asymptote at y equals 3. All right, this is slightly more complicated than last time, but it's not so bad. We also had a single critical number that we could plot, which was x equals 0, y equals 0, right there. And this was where the derivative is 0. So remember, when the graph goes through that point, it should be going horizontally at that moment. All right? Let's try and draw the picture. We have no other points to plot here. Let's try and draw the picture. So maybe start at this point and go off to the right. What happens as you move from this point and go to the right? Well, it must approach this asymptote, so it's either going to go up to heaven or down to HE double hockey sticks, as they say. Does it go up or down? That's the question. Look at the chart. In this region, it is decreasing, so it does go down, sorry to say, like that. All right? Great. What about to the right of this asymptote? Again, when you have these two crossing asymptotes, that means there's only two options. Just like in the previous example, it's either that or it's that, right? And which one is it? You look at the chart. It says in this region, it is decreasing. So actually, it's this one, right? Because that one is increasing. So it's not this one. It is that one. I'm feeling pretty good about this. How about right here in this region to the left of the point? The function is increasing, and then it must enter this point horizontally. It means it's coming up, and then it finally arrives at that point. So it's got to look like that. And then finally, over here to the left of the leftmost asymptote, the function is increasing. That means it is going up in this area. Remember, we have only two options. If it's going to respect the asymptotes, it's either that or that, and we choose the one which is going up as you move to the right. It's this one up here. So not that. Yes, indeed, this one. There you go. That's the graph. I checked this on my computer. Check it out. Looks pretty good to me.